Great, thank you all for being here, and thank you for allowing me to speak to you today. My name is Daniel Kowal. I'm a PhD candidate at Cornell University in the Department of Statistical Science. When I graduate, I'll be headed to Rice University, to their Department of Statistics as an assistant professor. So I like to mention that whenever it's cold outside like today. So the talk that I'm presenting today is based on methodology that has been published for a little while now. So the paper corresponding to this talk is up on my website. It's also up on the JASA website as well. What's new today is the accompanying R package, which I just put up on GitHub a couple days ago. So the general topic here is modeling functional data, so curve observations or points sampled from a curve, such that these curves are dependent. So I'll motivate that with an application, but we'll be thinking about a time series of functional data today. So real quick, here is just the source for my package. The source functions associated with it I've been working on those for a long time. The package itself is new, so some of the documentation may be a little bit sparse, but I'll work on that in the coming days and weeks. So as a motivating application, I'm going to be considering multi-economy yield curves. So here I have a yield curve. So this is a term structure of interest rates. Right, on the x-axis here, I have the time to maturity in years, so the length of the borrowing period associated with the bond. And on the y-axis, I have the yield. So this is for government bonds, in particular from the publicly available Federal Reserve database, but we could look at other interest rate curves as well. So as with most yield curves, it's positive, it's upward sloping, and it has that curvature to it as well. So we observe this curve, a single curve observation, points sampled from this curve at a given date. So this is November 8th. So the dashed line here is a yield curve from 1 week later. So November 8th, of course, was the US presidential election. People don't talk about that enough, so I'm bringing it up here. That's all I'll really say about it. It's just an interesting time point. In any case, this dashed line, you can see there is a change, right? There's a shift upwards, but there's also a bit of a tilt as well. So there are different types of dynamics in how this curve evolves over time. So we can roll this forward, right? We have daily data publicly available from the Federal Reserve. And so at each time, we have a curve, and we have many time points. So we have a time series of curves. You can also look at different types of interest rates, right? So this lighter colored curve is the publicly available Bank of England yield curve on those corresponding dates. So at a given point in time, you observe many of these yield curves across different economies or across different asset classes. And they're likely to be contemporaneously correlated. So you could model at a given time point the correlation across these different curves and model how these curves evolve jointly over time. So in this general setting, this multivariate time series of functional data, we have three dominant structural features. First of all, we have curve observations. The underlying observation, it's convenient to think of it as a curve. Secondly, we have time dependence due to the time ordering from one day to the next. And there's contemporaneous dependence as well between these multi-economies. So the methodology is developed for all three types of dependent structures. The package, as it sits now, is just for functional time series, so I'll focus on those today. So the general approach that I take is to extend dynamic linear models, or state space models, which work exceptionally well in the multivariate time series, to the functional data setting. So the model that I've developed is called the functional dynamic linear model, with that in mind. And it has something that looks like a usual basis expansion for functional data, but we'll see it's a little bit different. So the YT of tau here, that's our yield curve. So that's at time t. T denotes the time index throughout, and tau will be the functional argument. So it's a yield curve on day t at time to maturity tau. We write that as a linear combination of basis functions, fk. Now you notice those fk of tau, those only depend on the time to maturity, with corresponding weights beta kt, which only depend on time. So you have this time series of curves, and you're decomposing it into a small number of only functional components and only time series components. So it has this nice decomposition to it. What we'll do is we'll actually model these FKs, this functional component, as unknown. We'll model them as smooth unknown curves so that these important shapes will be different for different types of yield curves or different applications in general. It'll make this more broadly applicable. It'll also make it more adaptive to different data sets. So we'll model those as smooth unknown curves, and the betas will model those as a state vector in a dynamic linear model. So the machinery for that is well developed. Another way to think about this is as a factor model, in particular, a dynamic functional factor model. Right? Those FKs, those are loadings. We'll model them as curves, smooth unknown curves, so we can call them factor loading curves. The betas are the factors, and of course, we'll put a time series on those as well, a time series model. So we'll call them dynamic factors. And here, K is the number of factors, something that has to be specified. So we can make this a little more concrete by considering actual observations of the data. So here, this vector notation up here, that's my yield curve, the points along the yield curve that I observe at time t. So tau 1 through tau m, those are just the times to maturity that I observe. So for functional data, m might be quite large. It could be in the hundreds. Tau 1 to tau m, those don't have to be equally spaced for functional data. It doesn't even have to be the same across time. I'm just assuming it's constant here for simplicity of notation. So I can vectorize that observation equation that I showed on the previous slide. And so we have the data, which is an m-dimensional observation at time t. This matrix F, that's our matrix of those factor loading curves. Right, so at each column is Fk, evaluated all of our m observation points. So the point here is we may observe many, many points along the curve, but k is hopefully very small. That's the dimension reduction that we're doing. So that F matrix is going to be a very tall, skinny matrix. The reason that's particularly helpful is because this beta vector here, beta t, that contains the time series information in the model. That's the dynamic component. So rather than modeling something that's m-dimensional, which could be in the hundreds, we model a time series that's 3 or 4 dimensional. So that's a lot easier to do. It typically improves forecasting and estimation efficiency as well. So this looks like a fairly straightforward dynamic linear model or a state space model, right? I have my evolution equation down here, the beta t. And that could be a vector autoregression. It could be something simpler, like a random walk if G is the identity. And because we're operating within this dynamic linear model framework, we can extend to things like covariates, stochastic volatility, change points, important things for broad applicability. To estimate this model, I'm going to end up using an MCMC sampling algorithm. So I'll implement a Gibbs sampler. That's particularly nice here because we want to estimate all these parameters jointly, right? As we build up this hierarchical model, plug-in estimates are not going to work nearly as well as a joint estimate. At the same time, we want to be able to do inference and have posterior distributions available for parameters of interest. So to make this even a little bit more concrete, you can see this one-to-one correspondence between the model I've written as well as existing R code for state space models. So I like the KFAS package. And without getting into too many details, they define a state space model in very similar notation. This YT here would simply be my T by M matrix of data points. So this would just be, I would just transpose that vector and then stack them up across all time points. And this SSM custom function just says define the observation matrix Z, which in my case is F, an evolution matrix, which in my case is G, and then the 2 variances that I have. So I'm not really explaining what those notations are, but it's simply just to show that there is the one-to-one mapping, and I can use this state space framework as the machinery for sampling, but also for forecasting and other things you may be interested in. So the challenging part is then estimating those factor loading curves, those unknown curves. Right? We can use the state space framework for everything else. We have to estimate these unknown curves. So I have K unknown curves. That's something like a non-parametric regression problem. So typically in those cases, you write your unknown function as a linear combination of basis functions. So here I have a known vector of basis functions, say B-splines, and an unknown vector of coefficients. So for each scalar valued function fk, I have a vector of unknown basis coefficients. That's going to allow these curves to take a wide variety of shapes. I can include a roughness penalty, similar to how we heard earlier in this correspondence between regularization and priors. I can include a roughness penalty via a prior. So it's similar to the roughness penalties you'd see for like a cubic smoothing spline. So simply by specifying a Gaussian prior and a basis expansion, we can accommodate very flexible curves, they'll be smooth, it'll be computationally efficient in that it'll essentially be a series of linear regressions to run. So it doesn't add too much computational time to this state space modeling framework. So I'll go through some of the big blocks of this MCMC sampler, just to, because that's the core of what the package does. So if you're familiar with a Bayesian implementation of dynamic linear models or state space models, a lot of this will look fairly familiar, right? There's one step where you need to sample the factors or the states of this model. So using a simulation smoothing algorithm, which is available in that KFAS package, you can actually sample these betas jointly across both K and time. So this giant block of parameters you can do in one step, which is very, very important for a Gibbs sampling algorithm. It really improves efficiency. And there are very fast algorithms to do that. So I have a function that I define FDLM factor, which is essentially just a wrapper for the KFAS function. It just redefines the appropriate observation and evolution matrices. Then, of course, there's another step where you update your error variances. And without getting into too many details, you can include stochastic volatility models, you can include scale mixtures of normal distributions there. So there is a pretty broad framework for generalization here. So those steps are fairly standard in state space models, right? Sample the states, sample the other unknowns, which are the variances. So the real important step here is sampling those unknown curves. And so I have a function that does that, written in C++, uses RCPP, so we made it as quick as we could. And it'll sample these basis coefficients. It'll constrain them to be orthogonal for identifiability, which will also speed up some computations elsewhere. So it's essentially adding one additional step to the traditional state space model implementation. So if you don't feel like going through that yourself, I do provide a default implementation of the model with this function FDLM. So it assumes a fairly simple form. It assumes we have constant, so non-dynamic observation and evolution error variances, so not always appropriate for finance data. And it assumes a random walk model for that evolution. So it assumes that G is the identity, kind of a starting point for a model. So you can read in yield curve data, which I also include in this package, both for the US yields and the UK yields that I mentioned before. And each of those comes with three objects: the data matrix, the tau, which is the vector of observation points, so that's the times to maturity that you observe, and then some corresponding dates to go along with those time index. So just as an example, you can restrict the dates to 2012, just to keep it a little bit shorter, because it is a daily time series. And then run the MCMC. So this function here is just taking in my T by M data matrix. So T is the number of time points, M is the number of observation points. It takes in the observation points, don't have to be equally spaced. I specify the number of factors, or at least the upper bound on the number of factors, if we want to include some sort of shrinkage prior on those. And then usual parameters for an MCMC, like the number of simulations and the burn-in. And I've kept those small just to keep this running quickly. And you can also specify the MCMC parameters that you want output. So beta gives you the posterior distribution of the factors, the posterior distribution of the factor loading curves, and so forth. So running this takes about 2 or 3 minutes. So that's for about a little over 1,000 time points and either 10 or 100 observation points, depending on which observation or which yield curve data set you use. So that's pretty quick for an MCMC algorithm. So you can interpret some of the output here. So here are the factor loading curves, right? So you'll notice these are a function of the time to maturity. So these are the model estimates of these important yield curve shapes that persist across time. And these have very familiar interpretations, right? One of these curves is something that's just simply upward sloping, something like a level effect, right? It looks like an average yield curve. So it's mostly going to shift the yield curve up or down, maybe with a little bit more of an effect on the long term. This second curve here has this short-term bump and then trails off downward at the end. It's sort of like a slope effect. You can see that it's mostly positive on the short end and negative on the long end. So if you think about adding that to the yield curve, it's going to tilt up the short end and push down the long end. And then finally, this later curve here also has another familiar interpretation as a curvature, right? Again, it's mostly positive on the short end, it's negative in the middle, and positive on the long end. So it'll push up the short end and the long end and pull down the middle part of the yield curve. So these are nice familiar interpretations that we work with for yield curves. You can include plots of the factors as well to sort of see how these yield curve shapes evolve over time, as well as posterior distributions. I've included credible bands on these. And you can see the bands are pretty tight. But for example, this is the overall level shift, and you can see there's this big jump, which we saw right around the time of the election. And this second one is that slope as well. So where we saw a jump and we saw a tilt as well. So both of those persist to varying magnitudes. What's particularly interesting here, though, is we can actually estimate the yield curve using the model. So I haven't made any no arbitrage assumptions. I haven't assumed anything about the form of the yield curve. I've just said it's a linear combination of unknown smooth curves with dynamic weights. So these points here are the points from those earlier dates that I showed at the beginning. And the blue line is the posterior mean under the model. So you can see it fits the data, fairly well. We also have in those gray bands, those are simultaneous posterior credible intervals. So we can do inference on these yield curves. We can also take functionals of these yields, and that posterior distribution, those uncertainty intervals, will propagate to whatever quantities we compute. So that's particularly important. You can also do out-of-sample estimation, or very similarly, forecasting under this model. So I just picked a day on which there was no yield curve data, so day after New Year's. So you can see these bands are a bit wider. It still catches the shape reasonably well. And I could, again, take functionals of this yield curve, or points along the curve, and as I compute other quantities with those, the posterior inference, the uncertainty, will propagate to those other quantities. So that's very important. You can do similar things with the Bank of England, which I'll skip over today because it's fairly similar. And I'll really just conclude here by saying it's a fairly general hierarchical framework for modeling a time series of curves, right? We can specify the time-dependent behavior using familiar state space models. But because we're estimating those shapes, that functional component from the data, it means this is going to be broadly applicable. And we've, in fact, applied this to various applications in finance and neuroscience, as well as astronomy. We also have joint estimation of parameters. When you have a complex model like this, it's important to estimate those parameters jointly. And we can do exact inference up to MCMC error. And of course, the efficient Gibbs sampling algorithm is available through the package FDLM. And if you have any questions or comments on that, please let me know. But thank you very much.